Hello everyone, this is Matthias Soldan from King Abdullah University of Science and Technology, presenting VLG-Net, Video Language Graph Matching Network for Video Grounding. Background and motivations. Semantic search through videos is a relevant topic tackled in recent years. It can enable users to search through unlabeled and uncurated corpus of videos via natural language sentences, allowing, for instance, to search for specific moments in videos we all store in our phones. Or it could allow for fast retrieval of relevant scenes in surveillance videos. Moreover, it can be adopted in pipelines for visual question answerings in untrimmed videos. Another relevant application of language grounding in videos is video editing. After collecting hours and hours of raw footage, professional video editors are required to manually tag each clip with additional metadata. Often, such metadata is a textual description of the visual content they recorded. This step is required as it effectively speeds up the editing process. However, this is an expensive and time-consuming step. Therefore, our goal is to aid the editors by allowing them to search through video clips via natural language sentences, effectively removing the need to manually labeling all the clips. Let's then define the task that we are solving. Given a sentence and a video, we aim at temporarily localizing or grounding the sentence within the video temporal boundaries. For instance, see the example. As showcased by this example, this is not a trivial task to solve, and it requires to properly model both video and language modalities, and effectively learn their multimodal interactions. Previous approaches generate coarse, independent proposals, and match them through simple operation against single sentence representations. However, we argue that a fine-grained alignment approach is needed, and therefore we seek to directly model and learn the alignment between each video snippet and each word in a sentence. So what is VLG bringing to the table? A new deep learning architecture that boosts the state of the art on the presented task. A new approach to multimodality fusion based on an algorithmic graph matching. And finally, we validate and thoroughly test our method on 3 benchmark datasets and ablate all model main components. Let's get to it. Video Language Graph Matching Network, or VLG-Net for short. Here we depict the architecture. VLG-Net comprises 5 main modules. The first one is the raw data representation, where pixel-level information and word-level information are mapped to vector representations. Then, a single modality representation block, which focuses on enhancing the modality-specific features. A cross-modality interaction block, where we adopt a new approach to multimodality fusion, followed up by a mask attention pooling that generates proposals based on the fused features, and finally a scoring module, which predicts the temporal endpoints for the grounding purpose. Let's start delving into the details of the architecture. Each video is modeled as a sequence of snippets, where each snippet is itself a short video comprising few frames. We adopt a deep convolutional neural network for encoding the snippet information to a vector. The sentence is tokenized, and each token is then mapped to a vector through word-to-vec method. Snippet features are then passed through a 1D convolution operation to map their feature dimension to a desired shape. In parallel, a set of LSTM layer is used to process the word vectors, which allow to aggregate context for each word. Next, the single modality interaction block adopts graph convolutional networks to model the local and non-local context and enhance the feature representation. Such enhanced features meet and interact in the cross-modality module, where our new graph matching operation learns the best policy for multimodal fusion. The output of the graph matching module is passed to the mask attention pooling that produces proposal feature. Such proposal features are then scored and ranked to obtain the final temporal predictions. In the single modality representation block, the video is casted as a graph, where each node represents a snippet and each edge represents a dependency between snippet pairs. For the edges, we adopt the GC-Next formulation, which defines 2 sets of edges. The ordering edge, which connects temporally sequential snippets and models the sequential nature of the video. These edges are fixed and predefined. Conversely, the semantic edges are dynamic and change as the training of the network progresses. These edges connect semantically similar snippets in the video, based on the similarity in the feature space. They allow to connect temporally distant snippets and favor aggregating non-local context. Similarly, the sentence representation is casted as a graph, where each node represents a token. For the edge definition, we exploit the grammatical structure of the sentence. We determine the syntactic dependency among each pair of words, and define a set of predefined edges to connect the nodes. Again, our modeling strategy is to exploit the inherent modality structure and favor semantical connections between nodes to learn a non-local context aggregation policy. The two modality features finally meet in the cross-modality interaction module. Here we construct a new graph, dubbed as video language graph, where a node is either a snippet or a token representation. And we define three sets of edges. Ordering and semantic edges serve the same purpose as in the GCNext module. Moreover, these edges only connect nodes within the same modality. Conversely, the matching edge has the purpose of learning the best alignment between the language tokens and video snippets. We can see on the right the high-level mathematical representation of the graph convolution operation. We invite the viewers to take a look at the paper for the mathematical formulation of all described blocks. Once the multimodality fusion is complete, the features are passed to the mask attention pooling module, which produces proposal features. This module takes advantage of a mask, shown as a yellow bounding box in the slide. The mask defines the clips to aggregate together to obtain proposal level features. This aggregation is computed on top of the video and language fused features and is implemented as a weighted average on the clip, where the weights are computed as depicted in the figure. Once the proposal features are obtained, they are mapped through an MLP network to a set of scores, which are used to rank the proposals and obtain the temporal endpoints for the grounding of the language in the video. Experimental results. We compute the localization performance on three widely used benchmarks, starting with ActivityNet captions. In this case, we achieve on-par performance with respect to recent state-of-the-art methods. However, if we look at the performance on tacos, we can see that we are able to achieve a large improvement across all metrics, with an absolute margin ranging from 7 to 11%. Strong evidence of the good design can also be found in the demo, where we improved the previous art up to an impressive 30%. We then set out to evaluate the contribution of all edges in our main component, the graph matching module. The first row of the table depicts the performance obtained on tacos using the complete formulation. Then we remove the ordering edge and observe a drop of 2%. Conversely, when removing the semantic edge, the drop increased to 4%. Finally, when removing the matching edge, the performance are entirely compromised. Please notice that although the matching edge is removed, the two modalities still interact in the mask attention pooling module. This ablation showcases the relevance of each edge and proves that the combination of all edges yields the best performance. Another ablation looked at various formulations for the mask attention pooling module, where all configurations differ by operations and consider input information. Learnable self-attention only uses the video snippet after graph matching module to learn the proposal aggregation policy in a self-attention manner. The cross-attention scheme used both the video and the language information, however computes the score through simple operations. Finally, the learnable cross-attention configuration yields the best performance, leveraging both the video and language for generating proposal features, and learning a projection function for computing the aggregation scores. In our paper, we showcase some qualitative results, which showcase the good grounding performance of VLG-Net. We visualize the matching edge for some examples. In the first case, the matching edge obtains high score for the word talks, while the person is talking to the camera, while the edge obtains a high score for the accordion later in the video. In another example, we see how the verb writing obtains high matching score throughout the whole video, effectively matching the semantic content, while words as camel and beach fire up when they become completely visible in the frame. This visualization sheds some light on what the matching edge is truly learning. Here I present to you the rest of the team, to which I want to express my gratitude for the hard work. Thank you everybody for your time and interest. Feel free to contact me for any inquiry and visit the GitHub page for the implementation of VLG-Net. Goodbye.